Hi, this is Shabana, working as an associate professor in the Chevron Engineering College, Chevron. Today, I want to discuss about the electrolyte concentration cell. In the last lecture, in the previous lecture, I discussed about the electrode concentration cell. And today, I am continuing about the electrolyte concentration cell. In this concentration cell, the electrolytic cell, it is comprised of two half cells, like in the same electrode concentration cell. But the same electrodes should be taken. And the concentration should be different. That means it is a cell consists of two identical electrodes dipped in the two electrolyte solution of different concentration, due to which the difference in the potential at the electrode and electrolyte solution in which it is dipped. That means whatever the electrolytic solution in which the electrodes are dipped, there is a difference in the potential at the electrode will be created because of the different concentrations. The source of electric energy in the cell is the tendency of the electrolyte to differ from the solution of high concentration to the solution of low concentration. As a result, the EMF of the cell, that is electromotive force of the cell, falls to zero when the two concentrations of the electrolyte becomes identical. In this, the concentration of the cell acts to dilute the more concentrated solution and concentrate the more dilute solution, creating a voltage as the cell reaches an equilibrium. Because as the cell reaches to equilibrium, then the concentration of the cell falls to zero. And this equilibrium is achieved by transferring the electrons from the cell with the low concentration to the cell with the high concentration. As I already told you that the two electrodes must be identical and it is dipped in the two electrolyte solution of different concentration. See here, this is a concentration, electrolyte concentration cell in which the two electrodes, this is one electrode and this is another electrode, but of same composition, that is the silver. Silver electrode is to be taken and it is dipped in the salt solution of different concentration. It is a left half cell having the concentration of C1 and it is a right half cell having the concentration of C2. And it is connected to the voltmeter, and the left side electrode which is present in the left half cell, it acts as an anode, and the right electrode which is present in the right half cell, it is connected to the positive terminal of the battery and it acts as a cathode, whereas the left half cell of the electrode is connected to the negative terminal of the battery. And between these two, a salt bridge is connected. In the salt bridge, ammonium nitrate is taken. And such type of cells are represented as Mn plus with a concentration of C1. That means this is a salt bridge representation, and whatever the left half cell in this, the metal should be represented first, afterwards its ions with a concentration C1, And right half cell representation, because the reduction takes place at the right half cell, because the cathode is present. First, the representation of the metal ion with the concentration C2 is represented first. Afterwards, the metal, whatever the metal which is present on the right half cell, it is to be represented last by separating with comma. So this is a general cell representation. Coming to the example I took, here is a electrode, silver electrode. Here the example, that is the cell representation is silver electrode should be represented. Afterwards, its ion in the form of Eg plus in the with the concentration of C1, and it is separated by the salt bridge, which is represented in the form of a two straight lines. Afterwards, the cathode representation should be represented there. Here, C1 and C2 are the concentration of the metal ion. Ag1 in the 2 electrolyte solution separated by a salt bridge. And the concentration of these two half cells should be taken in such a way that the concentration of the right half cell should be more when compared to the total concentration of the left half cell. Therefore, it is C2 is greater than C1. And for a spontaneous process, the electrode reaction is represented in this way. At the anode, I already told you that the oxidation takes place at the anode with the liberation of an electron. Therefore, the metal, that means the electrode, which is in the solid state, it gets ionized. And the metal is converted into its ionic form, and it goes into the solution of C1. That metal ion goes into the solution of the C1 with the liberation of electrons. And this electron is transferred from the region of higher concentration to the region of lower concentration. That is, from anode to the cathode, the electrons is transferred, and this electron will react with the metal ion, which is there in the concentration C2, and it is deposited the metal near the cathode. That means the process of the reaction takes place at the cathode is the reduction, and the overall reaction is, see here, this n electron and this n electron will cancel out each other. Therefore, Mn plus 2, see this metal in the solid state and the metal in the solid state will cancel out each other. And the remaining, whatever the metal ions are there, with the concentration of C2 and C1 will remains as usual. So this will be the overall reaction. Coming to the EMF of the cell, as we already know the formula of the EMF of the cell, that is E cell is equal to E right minus E left. Therefore, the formula towards the right half cell is E0 minus 0.059 by N log 1 by C2 minus E left. Formula is E0 minus 0.059 by 591 by N log 1 by C1. Therefore, E cell is equal to E0 value is constant. So the remaining part, that is, this should be taken as common. That is 0.0591 by N to be taken as constant log C2 by C1. If C1 concentration is equal to the C2 concentration, that is the concentration of the left half cell is equal to the concentration of the right half cell, then EMF of the cell is zero. This whole value will become zero. Therefore, that means the reaction is at equilibrium, or because it will be equal and the value will become zero. If the C2 concentration at the right half cell is greater than the concentration of the left half cell, then the electromotive force of the cell is positive. That means the reaction is spontaneous in nature. The reaction is spontaneous in nature. Coming to what are the uses and applications of the concentration cell? The concentration cell is used to determine the solubility of the sparingly soluble salt, and it is also used to calculate the valency of the cations. The valency of the cation is easily calculated by the use of the concentration cells. And it is also used to determine the transition point of the metal. And the last but not the least, it is also used to calculate the extent of corrosion in the metal. The rate of the corrosion of the metal can easily be calculated by using the concentration cell. Next, coming to the next topic, that is the glass electrode. What is a glass electrode and what is its construction of the glass electrode and the working of the glass electrode? We will study now. Coming to the construction, what is the use of glass electrode means? It is widely employed electrode or widely used electrode for measuring the pH by combining this electrode with Kalman electrode. See here, this is a Kalman electrode, and by connecting the glass electrode with the Kalman electrode with the help of the salt bridge. With the help of the salt bridge, the pH of the solution can easily be measured. And this Kalman electrode is used as a secondary electrode. And the glass electrode is made up of, see here, this glass electrode, it is made up of special glass, Corning glass, containing the composition of sodium oxide 22%, calcium oxide 6%, and silicon dioxide 72%. We are taking this Corning glass because of relatively it is having low melting point and high electrical conducting. The glass electrode consists of, that is about the composition of the glass electrode. Coming to the construction of the glass electrode, this glass electrode consists of thin glass bulb filled with 0.1 normal HCl and silver wire. See here, this wire is there inside the glass electrode, which is made up of the silver, and it is coated with the silver chloride. and it is immersed in the HCl solution. And whatever this silver coated with the silver chloride wire, it acts as a internal reference electrode. The glass electrode is represented by Ag, AgCl. When a glass electrode is immersed in another solution, that means this, the whole arrangement will be like this. When glass electrode, if it is immersed in another solution of unknown pH, this is we have to take the beaker in which we have to take the solution whose pH is to be determined. That means the pH is not determined. That type of solution we have to take, and the glass electrode is immersed in that. There develops a potential between the two surfaces of the membrane. Because inside the glass electrode, one solution is there, which is known as the HCl. And here, another solution is there. Because of the difference in the chemical composition of the solution, there develops a potential between the two surfaces of the membrane. The potential difference developed is proportional to the difference in the pH. The glass membrane of the glass electrode, see here, the glass membrane of the glass electrode undergo an ion exchange reaction. The sodium ion on the glass, I already told you that the composition of the glass electrode, it is having the sodium oxide 22%, silicon dioxide 72%, and calcium oxide 66% and 6%. In that, the sodium ion which is present on the glass are exchanged for the H plus ions present in the solution. The potential difference or the boundary potential difference at the interference is the result of the difference in the potential, that is E1 minus E2, developed across the gel layer of the glass membrane between the two liquids. The boundary potential is related to the concentration of the solution inside the glass bulb, that is, inside the glass bulb having the concentration of C1, and the concentration of the external solution C2, into which the glass bulb is dipped, and it is given by the relation E1 minus E2 is equal to RT by NF ln C2 by C1. In this way, the pH of the unknown solution is calculated by connecting with the Kalman electrode, which is considered as a second electrode. Coming to the advantages of the glass electrode, it is having a rapid response and it remains unaffected by the presence of oxidizing and reducing agent. And this glass electrode is easy to operate and not easily poisoned. And equilibrium is rapidly reached in the glass electrode, and the results are accurate. Coming to the disadvantages or the limitations of the glass electrode, it is fragile in nature, and its inability in the presence of high concentration of the alkali, and the glass electrode can be used in the solution with pH range of 0 to 10. That means if the solution is having the pH 0 to 10, that type of solution pH can be determined by the use of with the help of the glass electrode, because the electrodes are composed of special glass that can be used up to the pH 12. That means Whatever the solution which are having the pH below 12, it can be easily determined with the help of the glass electrode. Because the electrodes are composed of a special glass. Up to the pH 12, it can be measured. The resistance is extremely high. The second limitation is, or second disadvantage is, the resistance is extremely high in the order of 10 to 100 million ohms, which cannot be measured by ordinary potentiometers. A special electronic potentiometers have been used. So these are the disadvantages of the glass electrode. See, a pH determination. For the pH determination of the solution with the help of the glass electrode, the electrode is dipped in the solution. That is the first and foremost rule. And it is also usually combined with the reference electrode, that is a calmum electrode, to form a complete cell. That is the second rule. And the third one is the potential of the glass electrode varies linearly with pH. Therefore, the glass electrode can be determined. The glass electrode is equal to E glass electrode is equal to E naught plus RTLN H1 H plus concentration. Therefore, E naught is E naught minus RT value 2.303 RT by F pH. Therefore, E naught minus 0.059 pH at room temperature, that is at 25 degrees centigrade. So that is about the glass electrode, advantages, limitations, as well as the description and the working of the glass electrode. And the EMF of the cell cannot be directly measured by the voltmeter, because the internal resistance of the cell may absorb some of the available potential difference, and the chemical change involved may result in polarization. So the EMF can be accurately measured by potentiometer. To measure the EMF of the cell, the external EMF, which is just equal to the EMF of the cell, is to be taken. At that time, no current flow in the cell takes place, and the null point can be detected and confirm it by comparing this with the standard cell, which is known as Western standard cell. So this is about the glass electrode, and in the next lecture, I'll explain about the battery topic. Thank you.